Yeah, thank you, Daniela. Welcome back, everyone. Let me try to remind you of what happened 2 days ago in the third of my lecture series. We were going through the calculation of the one-loop four-point function of massless states of the type 2 superstring. Essentially gravitons, or if you are good in reading out the double copy pattern of the polarizations, it even has all the information of external B fields and dilatons. Yeah, so we were using the RNS formulation of the superstring, where the worldsheet variables contained worldsheet spinner, denoted by psi. This worldsheet spinner had a variety of different boundary conditions. It may or may not catch a minus sign as you go around the A cycle or the B cycle of the worldsheet torus. And we had to go through all the choices. And let's say one of the four was very special, giving rise to parity odd amplitude contributions. And those we ignored. They don't arise at 4 points. But you can ask me about how they enter 5 points and beyond. And then there were 3 even choices of boundary conditions left for the worldsheet spinners. And those, well, we needed to sum over. First of all, the partition function depended on the boundary condition, but also the fermion-Green's function, aka the Sego kernel, depended on that spin structure choice. And it's this spin sum which leads to tremendous simplifications. This is due to the fact that some spin structures are responsible for fermions in the loop, and other spin structures are responsible for bosons in the loop. I mean, space-time statistics. And well, the old school QFT wisdom is that bosons and fermions partially cancel one another. And it also applies here to the situation of strings. And here it's actually an infinite number of space-time bosons and space-time fermions which circulate in the loop and partially cancel each other's contributions. So these SUSY cancellations imply that there is no vacuum energy at one loop and also no 2-point and no 3-point function. Again, this is tied to being in the maximally supersymmetric type 2 theory, both to A and type 2B. And of course, I need to relax these non-renormalization theorems if I break space-time supersymmetry, say, via compactification. But yeah, here all of this is about type 2 in flat Minkowski background. R1,9, and perhaps there will be comments at the end about torus compactifications which preserve the SUSY. So in case of torus compactification, there's just a mild add-on, namely you put in some additional tau-dependent factor here. But yeah, I am getting towards reviewing the final result of that one-loop amplitude. After taking all of these supersymmetry cancellations together, we found that the four-graviton amplitude allows you to pull all of the tensor structures out of a single scalar integral. I mean, this is quite different to what you encounter at higher multiplicity or already at tree level. There, different polarization dependencies go along with different integrands, different functions of the moduli. But here, it's a single kinematic factor going all the way out. And then the leftover job is to deal with that integral here. So remember, the opening line is you integrate over M1, 4, moduli space of tori with 4 marked points. And we somehow split the coordinates of M1, 4, that we start with a tau integration, taking the modular parameter of the torus as one coordinate, and then some sort of keep the 3 marked points for later. There are only 3 independent marked points among the 4 because there's translation invariance and you can always fix somebody to the origin or elsewhere. Okay, and the title of the lecture is about modular invariance, and this answer here is doing full justice to it. We have an integrand for tau, which is modular invariant exactly in alpha prime. So alpha prime is hiding in these dimensionless Mandelstam variables. So the convention here is that these SKL are dot products of space-time momenta. So the alpha prime dependence of the amplitude is entering entirely through these SKLs here. And yeah, the way how they are sitting inside the tau integrand, well, the tau integrand is itself an integral over the three differences of mark points. And here you have the alpha primes, and over there you have the bosonic Green's function, for which I gave you a representation in terms of theta functions. Oh, yeah, actually also a second one in terms of lattice sums that I will review later on. But what matters is, this is a modular invariant function, or a Jacobi form of weight 0, 0. And so my claim about modular invariance, it uses the fact that the Green's function is modular invariant, that the measure for integration over mark points is modular invariant, and last but not least, also the measure here for the fundamental domain of SL2Z is modular invariant. Okay, so it's all of these pieces and properties that play together. Yeah, if there was more time, I would give you some glimpse of higher point functions. It's almost disappointingly simple that there are no other functions of Z here. For instance, no singularities as the points go together. Well, there is no singularity for Z1 against Z2, which means that there are no kinematic poles in the amplitude. There are no kinematic poles that in field theory lingo would correspond to a triangle diagram. But starting from 5 points, there will be kinematic poles, which in field theory interpretation is a box with a massive corner. And such singularities will come in at 5 points and beyond through certain Jacobi forms of non-zero weight. So they are fun to study on their own right. The simplest of them are derivatives of the bosonic Green's function in the first argument Z. And just approach me after the lecture if you want to learn more about these Z-dependent Jacobi forms in higher point amplitudes. So if you go enough up with multiplicity, starting from 8 points, there's every now and then also a holomorphic Eisenstein series showing up. So yeah, these integrands of one-loop string amplitudes are pretty inclusive and bring a lot together from the zoo of variants of modular forms that were introduced at the beginning of the lecture series. But okay, to make sure we are finishing in time, let me skip a detailed discussion of higher multiplicity and instead discuss methods to learn more about the alpha prime dependence of that one-loop 4-point amplitude. And this will take you into the realm of so-called modular graph forms, which are, well, in the first place, they are just a useful mathematical tool to perform low energy expansions in the SKL. But also, they carry a lot of fascinating mathematics. As I will explain, this is an infinite family of non-holomorphic modular forms that generalize the non-holomorphic Eisenstein series, and whose existence was initially completely bizarre to mathematicians. And after enough of dialogue between math and physics, there was some really impressive work from mathematicians to help us understand these modular graph forms. And yeah, I would say these were dialogues between number theory, algebraic geometry, and physics that were of great benefit, definitely to string perturbation theory, and I very much hope that also our math friends feel that their respective fields learned a lot from these encounters. Okay, so this is what the first half of today's lecture is about, modular graph forms, somewhere in between string theory and pure mathematics. Yeah, the way how they fit into the flow of this lecture is that they are intermediate steps of low energy expanding this 4-point amplitude over there. And we follow this separation of the moduli space coordinates into, well, z integral first and tau integral later. This is admittedly not fully accurate, and I will point out later that there are certain logarithms in S that we are missing like that. But if all you want is the low energy effective action to be discussed in the second half of the lecture, it's okay to integrate over the z's first. Okay, so we are massaging now the tau integrand over there, denoted by I. Keep the modular parameter fixed and see what happens if you integrate out the mark points on a given torus. And yeah, we furthermore go all the way to doing the alpha prime expansion at the level of the integrand for the z's. And this is perhaps a harmless move, because as I stressed, there are no poles in the Sij. So at tree level, for instance, you shouldn't do that when there are kinematic poles around. But here at one loop 4 points, you get away in doing this z integral order by order in alpha prime. So what is the z integrand? Well, as you can clearly see, this is an exponential. And to each exponential with some Green's function upstairs, you do the good old series expansion like that. And here I'm writing it out for one out of these 6 factors here. And of course, you need to do this series expansion 6 times. So this is the opening line. And then at each order in alpha prime or in each homogeneity degree in the Sij's, you will have to integrate, well, a couple of Green's functions. So the most general integrand that you get out of this game here is a product of Green's functions for all pairs of points, zk, zl. And well, all of them can occur with an arbitrary integer power n. So to do this semi-formally, there are integer exponents nkl, which are integer or possibly 0. And so the measure, you are seeing it over there. It's always that modular invariant measure. Okay, so modular graph forms are a device to organize this series expansion and this order by order integration over marked points. So clearly this can come across a bit chaotic first time you see it. And the idea is now to organize different terms here through a graphical bookkeeping. So let's visualize each term of this form via graphs. Let's use capital gamma for a generic graph. And well, these graphs contain vertices and edges, and we draw a vertex for each integrated marked point. And strictly speaking, you can even integrate in that point z1. I mean, it never hurts to also integrate over z1 with the same measure. It's engineered such that it evaluates to 1 if the integrand is constant. Okay, so there is one, we draw a vertex for each integration variable. And then for the Green's functions in the integrand, we draw edges. And now for each power of the Green's function, there is one edge. So between vertex k and vertex L, there might be multiple edges if that power is different from 1. So then for a given pair of vertices, it looks like there's a small banana graph with n edges. But of course, the graph can have up to 4 vertices. So I guess you can easily imagine 4 vertices with 6 different opportunities in drawing edges in between them. So it's, in very loose terms, a 6-fold banana graph that hops out in the most general situation. But instead of drawing this exhaustively general case, maybe I try to give you more intuition through something like that. So this graph represents certain contributions here. Namely, you can count a total of 4 edges, which means that there's a total of 4 Green's functions in the integrand. That between 2 and 3 appears squared to appreciate this double edge, and then the point 4 is only connected through a single edge with its friends. And yeah, so this is the integrand that follows from the graphical rules. And concerning the integrals, you only need to mention those points which appear as vertices, which are in that case 2, 3, and 4. Okay, so this is the bookkeeping we will use. And as the first service, this will allow us to neatly formulate a rule for the zeros, which contributions, well, are killed by the integral. But okay, one step at a time. So first of all, I want to make the definition. So with this rule here to translate between graphs and Green's functions, we call the entirety of all these d gammas modular graph functions. So this symbol d is just saying apply these rules here. And yeah, this definition was made in a seminal paper here, Doker, Gudogan, Green, van Hoof, though there were some earlier papers discussing examples of modular graph forms. And once more, for arbitrary graphs gamma, this object is modular invariant. Since all its ingredients are, namely the Green's functions for the edges and the integration measures on the vertices. So they are all modular invariant. There are as many modular invariants to pick up as there are graphs that you can draw. Okay, now let's go into more detail for the Green's function. Oh, okay, I'm just integrating for each vertex, and I'm lazy. I don't want to write out all these d squared z2, d squared z3, d squared z4. It's my personal method to compactify. I'm applying the vertex rule 3 times. Good question. Well, if I pull out the integral there, I would need to write torus O times 3, right? Sorry, I didn't mean to go into nitpicking. Yeah. Is the question answered? Are you upset because there are 3 integrals? Yeah. So the rule is for each vertex, do this integral. And I see 3 vertices, so I apply this rule 3 times. Yeah? Okay. Okay, I was about to tell you about the Green's function, or I was about to review its lattice sum representation, which comes in particularly handy. It's less useful to know about the theta function representation here, but it's extremely valuable to do a Fourier expansion with respect to the co-moving coordinates, which go as follows. Well, this formula you may not immediately recognize, But what I'm introducing here is two kinds of things. You did see in the past plenty of lattice sums over m tau plus n with integers m and n. I will just put them together and call it p. And this is what clarifies what these p's in the integrand are. Then this lattice lambda tau prime is a shorthand for saying, well, what was the range of the m and n's before? They were both integers, and please stay away from p equals 0. So to line up with earlier formula, we want to have all values m and n that are integers, and removing the origin, I guess, in formal mathematics is a set minus operation. Then what else do we have here? So for the marked points, I was advertising several times that I really like co-moving coordinates, which are real numbers u and v that you can take to be in the unit interval in case of a doubly periodic function. And if a function of z is doubly periodic, then it will admit a double Fourier expansion in both of u and v. And the Fourier coefficients with respect to u and v were exactly these m and n's in the momentum p over there. So from all of this, you can probably reconstruct that this funny Lorentzian inner product here, Zp, is nothing but this mv minus nu that you saw in the previous time that I wrote that formula. Okay, so this is from my point of view, most useful representation of the Green's function to perform these integrals. And to continue the sentence, interpret the Green's function as a Feynman integral on the torus. So you don't see an integral here, so I clearly mean a discretized version of a Feynman integral. And, well, Feynman integrals are famously divergent in many cases, but we don't need to worry about the infrared. Small values of the momenta are automatically taken care of because the origin is not summed over, and there is a, well, honest-to-God spacing between the origin and the lowest lying momentum. So it's not only discretized, but also infrared regularized. Feynman integral on torus. So it's a little bit as if we are doing quantum field theory on the torus with scalar fields. The Green's function here is the scalar two-point function on the torus, quite literally, because it's a two-point function of the embedding coordinates x mu of the superstring. And yeah, we just represent that scalar Green's function in momentum space, where, given that we are on the compact torus, we don't have a continuum of momenta, but we have a twofold discrete momentum. So this is how you can think about the game which is getting played here. We are doing perturbation theory on the torus, and you can morally view alpha prime as counting the loops on this torus QFT. It's of course dangerous to say loops here, because the headline is one-loop string amplitudes. So the space-time interpretation is of course a strictly one-loop amplitude in space-time. But in intermediate steps, we have this worldsheet as an auxiliary object, and on that worldsheet, we have a QFT on its own right, which has tree-level one loop and arbitrary numbers of loops. So I hope you don't confuse the two of them. And the safest way around is to refer to string amplitudes as being genus H rather than G loops. Then you bypass the ambiguity of the term loop. Okay. So this was the interpretation, and let's now go back to some mathematical properties. So we don't have any zero mode in this lattice lambda prime tau, and this was tantamount to a property that I imposed on the Green's function, when we constructed it on Wednesday, then this was part of my wish list. This is admittedly the more optional part of the wish list. What do you do with the zero mode? This is not as essential as double periodicity and modular invariance and short distance behavior. But there is no loss of generality in imposing that, because what if you shift the Green's function by a constant? So the putative extra constant will be accompanied by the momentum sum. And maybe I missed pointing that out, but we have momentum conservation. So you just get a big zero if you decide to shift the Green's function. So there's no loss of generality in imposing that. Yeah, and this absence of zero mode makes our life very simple. It simply means that the modular graph form of a simple line is 0. It just means integrate this one over z. So this integral over z will pick up the zeroth Fourier mode in both u and v, but there is no zero mode. Okay, so this is the first immediate corollary, but now comes the real deal. I can embed this into a bigger graph. So this is not just a single modular graph form that vanishes, but a huge infinite family. So here is the big mass slaughter. A modular graph form is 0 whenever the graph gamma is one particle reducible. For those whose QFT lecture is a couple of months or years back in time, a one-particle reducible graph can be made disconnected by cutting through a single line. Clearly, this one becomes disconnected if I cut through that line in the middle, but also this bow tie graph becomes disconnected if I cut through the line in the middle. So also for the bow tie graph, its modular graph form function vanishes by that rule. Yeah, so this is really useful. Yes, please. Uh-huh. And then there is another statement about the absence of zero. Are these statements the same statement? They are not the same. If I don't impose this, I can put whatever I want in the zero mode. It doesn't have to take the same functional form on P. Just imagine you write +2. Writing +2 means that the zero mode in the Fourier expansion with respect to u and v is 2. But what you should really stay away from, don't attempt to generalize this functional form on P to the P equals 0 vector, because it blows up. Does this make sense? Thanks. Okay, I told you about many modular graph forms that are 0. Hence, it's time to look at the simplest non-zero ones. So let's draw one-particle irreducible graphs. And among the one-particle irreducible ones, I claim that the simplest class is one loop with some number of edges. And once more, everything is about the genus 1 amplitude. And it's just somewhere within the subcomputation at genus 1 in the string loop expansion that we encounter a scalar field theory, which by itself admits a loop expansion. Okay, so this is one loop graph that you can draw with Green's functions between, say, 1 and 2. And using the rules to translate it into a mathematical expression, and furthermore using the Fourier expansion of the Green's function, you get Well, a product of two such lattice sums. And well, the only z-dependent thing is the plane wave. So there's a lot of extra noise that I can pull out of the integral. And here is the only thing that requires a non-trivial integration. It's these plane waves with inner product involving momentum and z. So there are two edges, therefore two Green's functions, whose torus momentum I call P1 and P2. These are summation variables. I can call them whatever I want. Yeah, so here you have one Fourier integral to do. And yeah, these are really no problem. I mean, this is, at the end of the day, imposing momentum conservation on the torus. So this essentially is a Kronecker delta, which checks out if the momentum sum is really zero. And if you don't see this straight away, an intermediate step in doing that is I can rewrite the torus integral with the modular invariant measure as a double integral over u and v, which simply goes from 0 to 1. So this is the reason that you are getting Kronecker deltas. And also this is fully in lines with the QFT intuition. You impose momentum conservation at each vertex. That's what's going on here. All right, so there's no more integral here, and instead we are getting sum over momenta, now raised to the fourth power, after identifying P1 with minus P2. You can drop the minus sign, because our integrands are always even under P goes to minus P. Okay, now, who is recognizing this object? You have seen it many times. There were even disputes what ES actually stands for. This is a non-holomorphic Eisenstein series. Previously, they were written with M's and N's downstairs. And here, in a slightly different notation, it looks like that. So this is non-holomorphic Eisenstein series. And yeah, more generally, following the same methods, one can easily show that one-loop graph with more edges, it's still giving you these non-holomorphic Eisenstein series. Oops, sorry that the blackboard is getting too small here. So if you are with n edges, then it's the non-holomorphic En. Or in graphical notation, okay, here try to be brave and draw an n-gon. So here, n1, 2, n minus 1, and so forth. This is on the nose En. You have n lattice sums over momenta P1, P2, dot, 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 Pn, but you have a lot of vertices that impose momentum conservation. And that's why only a single sum over P survives, which is the one that defines the non-holomorphic Eisenstein series En. Okay, so this delimits the first slice of modular graph forms. If the graph has only one loop, then you get a non-holomorphic En at an integer argument n. I can only integrate integer powers of Green's functions here. That's why n is necessarily an integer. Yeah, conclusion up to now is that non-holomorphic Eisenstein series are contained in modular graph forms. However, they take you far, far beyond. So let's now look at the new terrain, what comes beyond non-holomorphic Eisenstein within the space of modular graph forms. So the simplest way of departing from one loop is to draw a two-loop graph. And the very simplest two-loop graph I can imagine is this one. I go for connected ones because modular graph forms factorize if I draw a disconnected graph. Okay, so this, some people recognize it as the sunrise or sunset graph, is a special case within two loops. Let me first write out its definition. The definition is an integral, but by now we have seen that all the integrals can be trivially done in Fourier space. The integrals are doing nothing than imposing momentum conservation. And yeah, if the sum of momenta P1, P2, P3 is conserved at both vertices, it means that there is an overall momentum conserving Kronecker delta around. And now for each edge, there used to be a Green's function with momentum space representative 1 over absolute value p square. So it means that we have each of the three momenta in the denominator in an absolute value square. Okay, so this is not recognizable as a non-holomorphic Eisenstein series, but amusingly, this simple case of two-loop MGFs evaluates to a sum of Eisenstein E3 plus zeta 3. So the method that Green and Van Hoof used to evaluate this triple sum was consultation of Sagier. And this special case here exemplifies that Riemann zeta values can arise from modular graph forms. And if you furthermore give modular graph forms a vector space structure, you can say this is a difference. Zeta 3 is the difference between the sunrise graph and a triangle graph with one loop. So this is a very amusing corollary. Special cases like this one are teaching you that odd zeta values are also contained in MGFs. That's why you sometimes hear people say that modular graph forms generalize Riemann zeta values and in fact even multiple zeta values to the modular world. Okay, perhaps this was a little bit underwhelming. I promised going beyond En, and the only thing I gave you was some special numbers. Let's go for a more general two-loop MGF, where there is a intrinsically new dependence on the modular parameter. So let's do the general case at two loops, which goes beyond En and zeta odd. Okay, so what's the most general cartoon of a two-loop graph? So now I could, in intermediate places of these edges, insert more vertices. It doesn't look nice if I do it here, but yeah, here's my attempt. This is more or less a sunrise graph again, but now with more vertices inserted in the middle. And each vertex insertion means that there are convolutions with more and more Green's functions. So let's say the number of edges above is A. Then I have another collection of B edges there. And finally, there are C edges down there. Okay. So what is this? So once more, use the definition, put in a Green's function for each edge, and even for each edge separated by these 2-point vertices. And there is a hell lot of integrals, but also a lot of momentum conserving Kroneckers. So in the end of the day, most integrals collapse by momentum conservation on the 2-point vertices. And when the dust settles, there are only 2 independent summations. And for the sake of symmetry, I write them as summing over P1, P2, P3, and remembering that the momenta add up to 0. Yeah, same trick as here, but now the difference is that these convolutions within the segments here give rise to a higher power of P1 downstairs, higher power of P2 downstairs, and so on. So now I am having arbitrary integers A, B, and C in these, propagators. Yeah, so since it's quite tedious to keep on drawing that graph, let's introduce a notation, CABC, for that two-loop modular graph form. And sometimes there are simplifications, like here. Sometimes it is possible to decompose it into Eisenstein series and zeta values, but generically this is not possible. So the first time where this is not possible is at weight 4. But before getting there, let me tell you about Laplace equations. So this is about the Laplacian in the modular parameter. Well, we briefly spoke of Laplace equations in Z for the Green's function, but since this is the Laplacian in tau now, I'll try to keep this in my notation. The modular invariant Laplace operator goes like this. And by modular invariant, it means if you act on modular invariance, then also the result of applying the Laplacian will be modular invariant. And this is a natural thing to throw on modular graph forms. They are all modular invariant, so it won't be a surprise if the Laplacian produces more modular graph functions. And indeed, the Eisenstein series are eigenfunctions. Just hit them with the Laplacian and you get back the same Eisenstein series, and the eigenvalue now depends on the subscript s. So strictly speaking, you don't even need s to be integer for this to hold. I mean, you can check this Laplace eigenvalue equation solely in terms of the lattice sum, and you don't need to use that s is integer. But of course, as a nice side effect, it tells you about the Laplace equations of all one-loop MGFs. Okay, now after having introduced the CABC notation for the two-loop modular graph forms, those are obeying a Laplace equation close to this one, but there is a small catch. There is a source term on the right-hand side. It's an inhomogeneous Laplace eigenvalue equation. Namely, there is a source, which I will exemplify with a C211 graph. So for this case, the Laplace equation on that two-loop graph gives back twice itself, but it furthermore cuts the graph into smaller pieces, which you can identify as an Eisenstein E4, but furthermore minus the square of E2. So the general source for CABC functions under the Laplacian goes like sources are either a single factor of ES or products of two, ES1 and ES2. And of course, the weight is conserved that, for instance, the sum of S1 plus S2 is always equal to A plus B plus C. But there won't be products of 3 or more. So this is the general structure of the source terms. Yeah, so this very comprehensive discussion of Laplace equations for two-loop graphs was given in this paper by Doker, Green, Van Hoof. Good. This concludes the second series of examples plus comments. If there was more time, I would go ahead and resolve the tau dependence of this one in more detail. I mean, these lattice sums are good to manifest the modular properties, but they are not optimal to, for instance, do an expansion around the cusp. Like, what are the Fourier modes? This is not so easy to see from the lattice sum above. So one could easily go deeper into alternative representations, and some of which are integrals of holomorphic Eisenstein series. So this starts to become exciting at the two-loop level, where you can't just resort to tabulated properties of the non-holomorphic ESs. But okay, to make sure I'm finishing in time, let's go back to our original motivation. We had it on the bucket list to analyze the genus 1 string amplitude, and we decided to do a low energy expansion first at fixed tau. So remember, there was this integral over the marked points over an exponential full of Green's functions. And the leading term of that exponential is, of course, that where you take no Green's function at all. Remember, the measures were engineered such they integrate to 1 if the integrand is constant. And now, what are the subleading terms? So now we can heavily draw from our selection rule that one particle reducible graphs integrate to 0. So this means there is nothing at first order in alpha prime. You can't integrate a single Green's function. This was the intro example of one particle reducible graphs. So the first contribution comes at the second order in alpha prime, when the accompanying modular graph form is connected, or is here, one loop with two edges. Yeah, there's admittedly a little bit of jargon here. There's Mandelstam S variable. I mean, we are in the phase space of 4 massless particles subject to momentum conservation. So we have 2 independent Mandelstam variables, S and T. And the third one, U, is just given by minus S minus T. But I will make the permutation symmetry manifest, hence why I didn't eliminate all the U's. Yeah, at second order in alpha prime, you could imagine to draw 2 lines that are not touching, or 2 lines which are meeting at a corner, but both are one particle reducible and thereby integrate to 0. So the expansion reduces to enumerating all one particle irreducible graphs with a given number of edges, and then figuring out how in the polynomial structure in S, T, and U they appear. Frequently using S plus T plus U equals 0, but I guess the polynomial algebra is comparably harmless in comparison to that integration task. Okay, so this is everything up to and including the third subleading order in alpha prime. So this is the graphical notation. And of course, all of them I already gave you simplified expressions for. So let's insert what we learned about the one loop graphs and then the sunrise graph, which was simplified by Zagier. Oops. Now, these indecomposable two-loop MGFs starting with C211, they will show up starting from the fourth order in alpha prime. There are actually a couple of new features to be discussed at the fourth order. For instance, seeing that the string amplitude isn't analytic in STNU, seeing that it has log S's. There are ways of seeing that starting from the fourth order in alpha prime. But let's say my focus right now is to discuss the analytic dependence on alpha prime, namely those terms in the full-fledged amplitude that are power series behaved. And for that purpose, that's an excellent expression to process further. Yeah, this is the result of integrating over the marked points at fixed value of tau on a fixed surface. And clearly, the next task is to perform the tau integral. And also this, we will do order by order in alpha prime here. Okay, the measure is, not sure whether the measure is still on the board. It's the d squared tau divided by m tau square. And yeah, you can just view this as the hyperbolic metric on the upper half plane or the fundamental domain. So at the leading order in the alpha prime expansion, when we integrate the term 1, we pick up the volume of the fundamental domain, which is pi over 3. Yeah, there are probably many ways to do the computation. My favorite one is to identify the measure as a total derivative of the almost holomorphic G2 hat Eisenstein series, but I can't blame you if you prefer a different method. So leading order has just the volume. And now what happens at subleading orders? And well, the only tau dependence which you see up to and including the third subleading order is through an Eisenstein series. And here it comes in handy that they obey Laplace equations. So whenever you see an ES, then let's rewrite it as Laplacian divided by eigenvalue. In these eigenvalues, they don't vanish for the range of S encountered as modular graph forms. We have S equal 2 and 3 and later on higher. So there's never an issue dividing by S times S minus 1. And they give you total tau derivatives. Okay, so when integrated over the fundamental domain, okay, I guess here I must be very careful to not gloss over mathematical subtleties. In the first place, you get a boundary term. And it's a bit delicate how exactly you deal with a cusp. I mean, there is a lot of literature suggesting to first look at the cut-off version of the fundamental domain. So you find in a lot of papers an intermediate step which first introduces a cutoff and later takes L to infinity. So in intermediate steps, the boundary term will give you something from that cutoff if you work with that. But the net effect, if you really track the full amplitude's dependence on the cutoff, it will completely go away. So when the dust settles, they integrate to 0 after some careful discussion on, of the fate of this boundary contribution in intermediate steps. So for instance, this Doker-Green-Van Hoof reference has a discussion of that, or also in later work of similar authors. Yeah. So good news, At the end of the day, I can discard the E2 and E3 over there, and hence, up to and including the third subleading order, the genus 1 amplitude expands as follows. Up to this order, we have, with the notation from before, we can pull out the volume of the fundamental domain. And apart from the leading term, I need to track this zeta 3 here. I mean, there's no tau dependence next to this zeta 3. So also there, you will pick up the volume pi over 3. Okay, so from everything set up to now, you can take away this collection of results on leading order, and nothing at subleading, nothing at sub-subleading order, and the next contribution at sub-cube leading order in alpha prime. So in terms of low energy effective operators, that I will focus on in a few minutes, we can here extract one loop contributions to a curvature coupling R to the fourth, which is the tensor structure with polarization dependence that we pulled out. And from the subleading term here, we have an additional zeta 3 along with, well, how to think of ST and U in position space. All of the Mandelstams are quadratic in derivatives. So STU translates into a total of 6 space-time derivatives, and I'm writing capital D because in truth they will be diffeomorphism covariantized ones if I translate this into position space with all nonlinear completions of the Riemann tensor. Oh yeah, I have been sloppy in the overall normalization of the amplitude. So in my next life, I will write out the leading 2 pi in front of the entire one loop amplitude, which takes the pi over 3 into a rational multiple of pi square. Okay, and again, there is this disclaimer analytic saying that here we are only going after power series behaved terms, and we are not tracking the logarithmic terms. So another class of amplitude contributions goes like logarithm of Mandelstams, and you can easily see from unitarity that those are present and actually needed. So I think amplitudes, people often draw unitarity cuts like this, which are essentially telling you that the amplitude has discontinuities in ST and U, which are given by products of trees, left and right of the cut. And this is admittedly a cut of a supergravity diagram, but you can also cut diagrams with higher derivative operators. So for instance, there are R to the fourth higher derivative corrections at tree level already. So there are also cuts of this form, which contribute to log S. So that's why we have logarithms at arbitrary orders in alpha prime, simply because the tree amplitude has arbitrary orders in alpha prime. And all of those are systematically discarded simply because we series expanded in alpha prime in line 0. We series expanded the exponential of Green's functions as if the amplitude was analytic. And of course, it cannot end well if there's a non-analytic function and you expand it as if it was non-analytic. So it's not surprising that we are missing those terms. But on a positive note, there's a controlled way of missing the logarithms. It doesn't mean that we need to trash the computation here, but instead, the computation is 100% reliable to the orders I spelled out. And there's also work by Doker and Green to make this reliable up to and including the 12th order in derivatives, or 6th subleading order in alpha prime. Okay, so I think I'm essentially done with the modular graph form discussions. Again, this is just giving you a glimpse into that fascinating world of modular graph functions. What I didn't dwell on so far is that if you expand them around the cusp, if you make a double Fourier expansion like that, then following my general statements on non-holomorphic modular forms, you have functions of im tau that go along with the Q and Q bar expansion. And in modular graph forms, the number theory is such that these Fourier modes, in the generalized sense, have multi-zetas as coefficients. So you saw a Riemann zeta here, and also the Eisenstein series has Riemann zetas with an inverse power of im tau. But this goes much further. Not only Riemann zeta, but also multiple zeta values were diagnosed within the expansion of more complicated graphs. So there's a number theory reason to really like them, the multiple zeta values in their QQ bar expansion. Then the next thing is differential equations in tau. So we only looked at the Laplace equation where the tau derivatives were immediately balanced by a tau bar derivative. But you get a lot of complementary information if you keep on doing holomorphic derivatives, or more precisely apply those mass derivatives which preserve the modular form property. So from iterated mass derivatives that go essentially with this operator to some powers, you eventually recover holomorphic Eisenstein series. So there is a connection in between the holomorphic realm and that of the real analytic modular graph forms. Just do this operator sufficiently many times. So conversely, you can integrate back those differential equations. I alluded to this before. You can interpret modular graph forms as coming from iterated integrals over holomorphic modular forms. That's why I couldn't resist to make the comment in Roberto's lecture. These integrals are unproblematic in case of cusp forms. I mean, we typically integrate all the way to the cusp. And if you want to have a well-defined integral of gk up to the cusp, you need a good regularization prescription. And for all string theory applications of this, which I've seen so far, the tangential base point method of Francis Brown is doing the job. Okay, so it's good to write modular graph forms in terms of iterated Eisenstein integrals. And there are a lot of bells and whistles. You need to add their complex conjugates. You, strictly speaking, need to also look at the tau bar differential equation. And also, not every iterated Eisenstein integral is realized in here. So the modular graph forms are a proper subset in the bigger space of iterated Eisenstein integrals. And there are beautiful algebraic structures which select that subspace where modular graph forms are living. So for the mathematically inclined experts, these are certain derivations denoted by epsilon that act on the fundamental group of the torus, freely generated by two non-commutative variables a and b. And these derivations are in a certain sense dual to holomorphic Eisenstein series and have a long mathematical history going all the way back to, say, Ihara or Deligne. And they are often associated with the name Tsunogai, who discussed their action on the fundamental group of the torus in more detail, giving explicit formula and all that. And you can also ask my student Johan what they have to say about the structure of elliptic polylogarithms. Okay, and finally, this theory of combining iterated Eisenstein integrals with their complex conjugates and getting a modular object out of that, this was a question that Francis Brown studied, and he coined the term of an equivariant iterated Eisenstein integral. So this is about a collection of rules how to glue Eisenstein integrals with their complex conjugates and multiple zeta values. So there's a lot of balancing that you need to do such that they are really modular forms. So yeah, Francis wrote two seminal papers on that in 2017. Maybe not as many examples in there as we would have hoped to see, but I think by now in the work with Daniele and many others, I think we made substantial progress in making Francis this construction explicit. Good. That's it on modular graph forms. And now I should really switch to space-time modularity. So now there's a harsh cut. Please ask your questions on modular graph forms now. We can even consider a 5-minute break. Yeah? Oh, yeah. Well, I wish I had the time to cover that. It's for sure a fascinating subject, and yeah. Okay, welcome back. One of the reasons for the break is that it's looking less disturbing that we're making a heavy transition now. We leave worldsheets behind and now look at a completely independent incarnation of modularity in type 2B superstrings, namely a modularity that I refer to as space-time modularity, where the SL2Z acts on a complex scalar field, the so-called axiodilaton, and not on a modular parameter tau of a torus worldsheet as you saw it before the break. Okay, to give a bit of context and glue it together with the amplitude that you've seen before, I should clarify that string amplitudes enjoy a double expansion. There are two parameters they depend on that are worth expanding in. Namely, there is, first of all, the genus expansion with the string coupling G string as an expansion parameter. So there is a loop order which organizes different powers of G string, where from worldsheets of genus H, the power of G string is like that. And now the second expansion for string amplitudes is in the low energy order or derivative expansion. So here it's alpha prime, which governs the second type of expansion. Yeah, so all this to say, you can draw a two-dimensional plot about the double expansion of string amplitudes in genus, which could go into this axis, and simultaneously in low energy orders. So let's put the orders in alpha prime into the y-axis. And what you have seen before the break and in the previous lecture was a detailed discussion of the genus 1 amplitude. And we even got to the point of tracking a few orders in alpha prime. So what you have just seen before the break was we identified the low energy limit, which was something about a fixed order in alpha prime, plus many, many higher orders. And I think I went with you up to and including the third subleading one, from the examples that were worked out in front of your eyes. And that integral representation, which you saw, is in principle carrying you to arbitrary orders. If you're powerful enough to deal with the z and tau integrals, then you have a semi-infinite line in this double expansion from that torus calculation we did. So this is what you saw before the break, and now we rotate by 90 degrees and do something else. We are now looking at a slice at fixed order in alpha prime and want to cover the exact dependence on G string. No longer separating different genera, but ideally unifying them. So it turns out that at low orders in alpha prime, there's only a finite collection of terms, up to and including here. But it's an ongoing debate whether these strips here truncate at higher orders, possibly not. But yeah, what I will discuss now is looking at these green orbits, where we fix the order in alpha prime, where we lock in a given higher curvature correction like r to the fourth, and where we will debate the exact dependence of its coefficient on the string coupling. Yeah, so this is the difference of before the break and after the break. We were previously looking at the red orbit in this direction, and now we are going for the green orbits perpendicular to that. Oh yeah, my universal excuse is that I wrote a proportionality twiddle when I gave you an expression for the amplitude. Put as many alpha primes up front such that it makes sense with your personal counting. But the most invariant way of justifying the 3 here is to say that I'm counting relative to the supergravity. So this is to say that I'm 3 alpha primes away from supergravity here. Yes. True. Yeah, it's not so in. Yeah, there is supergravity probably here. Yep. Mm-hmm. Okay. Yeah. Oh, it's an artifact of my drawing. I didn't intend to comment on it, but Hynek's question was a good motivation to do it, and now I'm paying the price for my space economy. Yeah. Okay, and now this tracking of exact G-string dependencies, this is traditionally done not at the level of amplitudes, but more at the level of low energy effective actions. This is, in a nutshell, a Lagrangian equivalent of encoding the information in an amplitude. Low energy effective actions are an attempt to reconstruct a given amplitude from a Lagrangian and higher derivative terms therein. So the low energy effective Lagrangian is defined to reproduce the analytic terms in amplitudes in various endpoint H loop amplitudes via Feynman rules, or your favorite method of converting a Lagrangian into on-shell amplitudes. Okay, and yes, please. Can you ask me this question in 5 minutes? I'm writing a formula then, which has a potential to answer your question. Maybe it's already happening here. So a part of this effective action will be supergravity. As long as we are dealing with type 2a or type 2b superstrings, it's the corresponding type 2a or type 2b supergravity. whose bosonic part in the supergravity Lagrangian, or whose purely gravitational part, is the good old Einstein-Hilbert. So this is a statement about the leading order in alpha prime, and I'm extremely lazy here. There is so many supersymmetry partners that I'm truncating here. So here I'm just writing lovelessly SUSY completion, which refers to B field, dilaton, Ramond-Ramond forms, Gravitini, Dilatini. So there is a lot in here, but all of them are just supergravity plus superpartners, the invariantization in type 2a and type 2b supergravity. Okay, so this happens at the leading alpha prime order of such an effective Lagrangian. And then comes the tower of alpha prime corrections. And their onset in case of maximal SUSY, type 2a and type 2b, is at the third subleading order. So in semi-explicit terms, we have 3 or more additional alpha primes together with higher derivative operators. So the simplest one that you keep on seeing is r to the fourth without any derivatives yet. But if I additionally isolate Mandelstams in an amplitude, this means that there are additional space-time derivatives, which are, of course, at even higher order in alpha prime. Now, so far you have only seen 4-point functions. In principle, there's also a question about r to the fifth and higher curvature corrections. They are sometimes interlocked by nonlinear supersymmetry with r to the fourth, but not always. And this is one motivation to independently compute higher multiplicity amplitudes, apart from the overall recursive structure that one loop higher points feeds into 2 loop lower points. And again, this is just the tip of the iceberg. There is a gigantic tail of SUSY partners for r to the fourth, both in the same R symmetry sector, like, for instance, the Ramond-Ramond 5 form coupling. But there are additionally some charged counterparts with alike axiodilatons, or my favorite example, 16 dilatini, which are related by supersymmetry to r to the fourth, but which carry a lot of U1 charge. Yeah, so there's really a lot in here. I'm not at all doing justice to that important problem of spelling that out. Okay, and why is there a jump between supergravity in the third subleading order? It's simply a matter of maximal SUSY, which rules out everything in between. So how could you saturate a single alpha prime relative to supergravity? This would be 2 powers of Riemann-Ricci curvature, and that is forbidden by 32 supercharges by the maximal supersymmetry of type 2b superstrings. And yeah, maybe you know these things from the bosonic string. Without supersymmetry, they are fine, but here in case of the 32 supercharges of type 2, all of these operators are a no-no and therefore don't appear. So condensing all of that into a schematic form of the effective action going beyond supergravity, we will have beyond Einstein-Hilbert this tower of operators that pass the selection rules from SUSY. And now the challenge is to fix their exact dependence, well, first of all on the string coupling, but in the bigger scheme of things, you specify their coupling as a function of moduli, or every scalar in the theory is allowed to have a VEV without violating Lorentz invariance. So each coupling is, strictly speaking, a function of all the scalar VEVs. So all of these couplings are now denoted with a calligraphic E, and the full task is to resolve these functional dependencies on the moduli. Okay, again, I keep on suppressing SUSY partners of pure curvature corrections, and I'm again stopping at a not particularly high order in alpha prime, hoping that this is enough to give you an idea. Yeah, what I just said in words, all of these couplings, here collectively denoted by calligraphic E bullet, depend on scalar VEVs. And it's good that we are in type 2b, because in type 2b, there's enough scalars to have a non-trivial dependence, but few enough scalars that we can control it. Namely, these are the Ramond-Ramond axions, or there's one Ramond-Ramond axion, sometimes denoted by C0, and then the Neveu-Schwarz sector contributes one scalar, namely the dilaton. Yeah, and this notation omega refers to the complex combination of those two, also called the axiodilaton. So the couplings are separately for each higher derivative operator functions of this axiodilaton. Okay, I think I'm now at that point where I believe I'm in better position to answer your question, but I forgot the question. Oh yeah, it doesn't truncate. I mean, there are operators to arbitrary orders already at one loop and tree level. Ah, yeah. Yes, there's a non-renormalization theorem for the d to the 6 r to the 4th operator here. And it's an ongoing debate to which extent there are more operators up here which enjoy non-renormalization theorem. In the round bracket, you mean? Ah, okay, the square bracket is at fixed order in alpha prime, but maybe, since you're asking about the horizontal line, this is about the functional form of the calligraphic E's, which I will elaborate now. Okay, now it's the moment to recall S-duality, or to define it properly. So the type 2b theory enjoys a self-duality under a certain move on the axiodilaton and other fields. It enjoys an invariance under SL2Z, and I will just use the same notation as before for the 2x2 matrix representation of SL2Z. So this symmetry of type 2b is called S-duality, and its action is easiest to spell out on the axiodilaton. It just performs the same type of modular transformation that you typically see on worldsheets. So this SL2 pretends that the axiodilaton is a modular parameter of a putative torus. And part of the symmetry of the theory is to transform the axiodilaton field like such. And there are similar transformations for most of the superpartners. For instance, there are three forms, one from the Neveu-Schwarz sector and one from the Ramond sector. And also these three forms are rotated into one another under SL2Z. But importantly, the graviton happens to be in an SL2 singlet. So SL2Z acts trivially on the graviton. And also alpha prime is invariant under this. Maybe this is the even more important message. Okay, and here, these invariances of both the graviton and alpha prime has two crucial consequences. Namely, since alpha prime doesn't transform, S-duality holds order by order in alpha prime. So in terms of this plot here, I can impose S-duality not only once for the entire plot, but instead we impose S-duality on each of the horizontal lines. And this really covers whatever it takes to reproduce the exact dependence on the string coupling, namely modular invariant function of the axiodilaton. And now that we introduce this notation calligraphic E for the S-duality invariant couplings of various curvature corrections, we introduce notation E for the couplings, and by S-duality, they must all be separately modular invariant. So all of these E bullets seen here and all of them which will appear at higher order, they are all separately modular invariant. Okay, so the quest is essentially to sort out modular invariants that fit to various terms in this low energy effective action. Now, let's be more precise how exactly the dilaton is lying in there and how it relates to the string coupling. So the string coupling is just covering the imaginary part of this complex omega. So the string coupling is the inverse imaginary part to be fully exact, and it is set by the vacuum expectation value of the dilaton. So the string coupling doesn't care about the axion C0 sitting in the real part, but it's set by the imaginary part. So as an immediate corollary, if I ignore the axion for the moment, then the modular S transformation, which as before sends our complex modular parameter to -1 over itself, this modular S transformation simply swaps weak coupling and strong coupling. So this, at the level of the imaginary part, just leads to an inversion like such, at least in absence of axion. So that's why, to zeroth order approximation, you can view S-duality as strong-weak coupling duality. But this is by no means exhausting the power. I mean, it's just one generator of the modular group. There is, of course, now the additional T generator and all the interplay between axion and dilaton. But one of the reasons that I'm stressing here that story, that string coupling is about the imaginary part, there's a mathematical reason to dwell on that. Namely, let's recall the Fourier expansion of non-holomorphic modular forms. Even though I haven't told you yet why these calligraphic E's are non-holomorphic, let's just go for it in view of the greater generality. So for non-holomorphic modular forms, there is a double Q expansion, Q in Q bar. Fourier expansion is strictly speaking in the real part, but apart from the periodicity in the real part, modular invariance is compatible with having functions of im omega at each order in the Q and Q bar expansion. And a priori, you could also study incarnations with a pole at the cusp. But here, for S-duality, let's make sure that the function is smooth at the cusp. Otherwise, the weak coupling regime would explode and string perturbation theory would crash. So this is to explain why we start at 0, to have a good perturbative regime to be smooth at weak coupling. Okay, and now Q, well, before Q was e to the 2 pi I tau, but you probably guessed that this is now 2 pi I omega in the exponent. And importantly, if I rewrite this in terms of the string coupling, you find e to the minus 1 over G string. So this is the infamous function that doesn't have a non-trivial Taylor expansion. I mean, tailoring that is 0 to all orders. This is a non-perturbative term. This is something you can never ever see in string perturbation theory. Vanishes at all orders. So the consequence is some sort of a lesson in modesty. What can the perturbative string amplitudes tell you about all of this? Even if you have infinite power to go through all genera to all orders in alpha prime, you would still get nothing else than the A00. You would only get those terms which have neither a Q nor a Q bar, because both of them are completely flattened out by the perturbative expansion. So it's almost disappointing that perturbative string amplitudes don't take you that far, that they only probe the A000. But on a positive note, this A00 can still depend in exciting ways on the imaginary part of omega. So it's not just a number, as it would be in the holomorphic case, but it can still be a function of omega. So there's still room for having contributions from various loop orders, possibly even an infinite number thereof. Okay, then let's skip the distinction between string and Einstein frame and just go into the Einstein frame action. So if you scan the literature and pick up all alpha prime expansions that are presently known, up to and including the 3-loop order. So again, this is the 4-graviton amplitude at various loop orders. Then you can reverse engineer the following contributions to the type 2B effective action. So now this will be almost the same expansion as seen over there, but now it's getting a bit personal. Instead of an unspecified E bullet, along with various operators, I'm now spelling out the contributions to these E-bullets that are known up to date. So for instance, at the R to the fourth case, you have seen it, how the one-loop contribution can be computed. And if you get the normalization correct of the overall amplitude, it's indeed a 4 zeta 2 and not just a pi over 3. So this is the one-loop contribution. And now, the denotation is obviously that omega 2 is the imaginary part. And if you are surprised that one loop is not coming at the 0th power, here is a subtlety known as the conversion from string frame to Einstein frame. So you would, in case of a tree-level contribution, expect 1 over g string square, which is omega 2 square. But here I'm writing 3 over 2. So what's the catch? Why not this? And you have at some point to rescale the metric and therefore also the Riemann curvature to get a canonical kinetic term. And this rescaling is said to take you from string frame to Einstein frame. Yeah, just ask me after the lecture if you want to hear more details. And yeah, this conversion factor from string frame to Einstein frame, it has a different effect at different orders in alpha prime. It's really not a big mystery, but I just wanted to say or explain why tree level is not always giving you omega 2 to the second. Yeah, so here this is the next non-vanishing order, which is a d to the fourth, r to the fourth with alpha prime to the fifth. And here the contributions are from tree level and two loop. So we saw from the discussion of modular graph forms that there is no one loop contribution to that fellow. The putative contribution would have been the integral of E2 over tau, but in view of the Laplace equation, this was 0. Okay, and the last series of contributions that I can report on are here for d to the 6, r to the 4th. So there we have contributions up to and including the 3-loop order. Yeah, and all of them have been matched with amplitude calculations. So the last one is a 3-loop amplitude at the low energy limit. Okay. So this is everything that we can get out of perturbative string amplitudes so far. I have not written anything about the Q and Q bar corrections over there, which are to be interpreted as instanton contributions or instanton anti-instanton pairs. And usual disclaimer, I'm not tracking superpartners and I'm cutting off at a given order in alpha prime. All right, so this is just the A00, but S-duality tells us that there is a modular invariant function of the axiodilaton, which has this as its 0 mode. So now the next step is a detective game to smell which modular invariant is kind enough to give us those terms from their 0 mode. And in 2 examples, there is a very simple answer to this. Oh, I shouldn't have started to wipe that out, because these are the symbols to denote the full coupling of r to the 4th. So calligraphic E3 is meant to be the modular completion of the 2 perturbative terms for r to the 4th. And similarly, there is a notation calligraphic E33 for the modular completion of the bigger chunk of terms here. So this is the zero mode of some modular invariant E3 in the notation of over there. What are these modular invariants? And good news, two of them are non-holomorphic Eisenstein series. And maybe I give you the A00 not only of ES, but maybe I instead give it for a rescaled version with the power pi to the S sneaked in. Because then this is nicely giving a zeta value. Here is the first contribution to A00, some positive power of im omega. And then there's a second one with a negative power. Which has again a zeta value, but now 2s minus 1. And that one. Okay, and everything else has either a Q or a Q bar. So these are terms which are non-perturbative from the viewpoint of type 2b effective action. Infinite series, but not visible to perturbative string amplitudes. But we know that this is modular invariant. You saw its lattice sum definition. So it's actually a bit of work to go from the lattice sum to a QQ bar expansion like here. If you want to see the details, these are K-Bessel functions that were mentioned and discussed in other lectures. Okay, and yeah, if you now compare this with the examples above, it matches perturbative terms of, well, first of all, r to the fourth has these two perturbative terms which are exactly reproduced by the Eisenstein series E3 half. And there is a second successful strike, also the coefficient of d to the fourth r to the fourth. Its perturbative terms are fully accounted for by E5 half, up to some boring rescaling with pi. So these two examples point into the following pattern. Non-holomorphic Eisenstein series appear in two places. The argument is half-odd integer here, and this is about the space-time modularity. And there was a second appearance in string perturbation theory, modular graph forms. This was when the argument was integer, or integer plus 1. This was under the flag of worldsheet modularity, or more specifically, modular graph forms. So it's quite amusing that it's one and the same function E of S, the non-holomorphic Eisenstein series, but depending on the context, you either specialize to integers on the worldsheet or to half-odd integer in space-time. And admittedly, this is rather weak evidence. Why should this be the full modular invariant answer? It's modular invariant and matches the zero mode, but maybe I should work harder to convince you that this is really the right answer. And a third piece of evidence comes from the Laplace equation. So you saw before the Laplace equation of non-holomorphic Eisenstein series. Eigenvalue s times s minus 1 under the modular invariant Laplacian. And one can derive from space-time supersymmetry a Laplace equation for those two objects. And this Laplace equation is also exactly fitting to E3 half and E5 half. So this is a third element of evidence that these expressions have correct modularity, correct zero mode A00, but also correct Laplace equation. And there's indeed, this would have been my next sentence. There happens to be a theorem that these three observations jointly imply uniquely that this is the right answer. There is no more escape if you specify all of modularity, Laplace equation, and perturbative terms. Yes. Okay, so this is the modular completion to most of the stuff on the board. But we have not yet poked on the last fellow that is written out, the coefficient of d to the 6, r to the 4th. So maybe you can anticipate from the notation chosen that this is not an E6, but an E33. And also that one obeys a Laplace equation, but it's unfortunately not homogeneous anymore. So instead, E33 is solution to an inhomogeneous Laplace eigenvalue equation, namely Laplacian in modular parameter omega minus 12. And now it has a source term, which is again quadratic in Eisenstein series. So the structure of the source term should remind you of what you saw in the MGF situation. So I quoted a Laplace equation in tau for some of the MGFs. One of the two-loop modular graph forms had a Laplace equation with a source term involving E2 squared. So it's a common theme, once more, between worldsheet modularity and space-time modularity, that you should study Laplace equations, eigenvalue equations, with a source term that is bilinear in non-holomorphic Eisenstein series. So this is, in a certain sense, extending that correspondence from depth 1 to depth 2. And it's for this reason that we expect modular graph forms to be a good toy model for all the higher orders that are not spelled out here, all the not yet known S-duality completions at 7th order and alpha prime and beyond. So this is a big open problem, and maybe this workshop here helps to get a step closer to its solution. Okay, I guess I should stop here. Sorry for the time management. Thanks.